Hello, this is Dave again, and in our last video we were measuring how fast is my algorithm, and specifically how fast is it. We want to know intrinsically how efficient it is, how fast it is, how much time does it use up. We don't actually care what's the actual time on a particular processor when the program is written in a particular programming language. We want to measure intrinsic efficiency, and we found that the way to do that is to determine how does the running time depend on the size of the problem. Usually I'm dealing with a problem, for example, the length of an array might be the size of the problem. Maybe if the array gets longer, I consider that to be a larger problem, and I want to know how much longer will it take to solve the problem when my array is longer. And we found two answers so far. It could be that the time does not actually depend at all on how large my problem is, and we call that constant time. Or it could be that the time is roughly proportional to the size of my problem, meaning that if I double the size of my problem, it will take twice as long to solve it, and we call that linear time. And the last method we looked at was, let me leave that on the screen. Last method we looked at was count matches, which determined how many times does this particular value appear in my array, and to do that we looped over the entire array. We checked each element to see if it matched that value, and if it did, we added one to the count, and we did that over and over again. And we said that the time for this method was indeed linear in the length of the array. If the array is twice as long, it will take twice as long to test all these values because there will be twice as many values to test. And it may have bothered you that this line, count equals count plus 1, doesn't actually run every time. But it turns out if we take this line out, if we say, let's say the best case scenario, best case is there are no matches, because if there are no matches, we never get to this line. Well, in that best case scenario, it's still true that the number of values I test is linear in the length of my array, and my time is therefore going to be linear, so I will still have, oops, I'm not going to use that notation yet, I will still have linear time. Then we could consider the worst case, and the worst case is all matches, every single value matches. And if every single value matches, it turns out by the exact same logic, I can conclude it will take linear time. If my array is twice as long, it will take twice as long. Let me do this. It will take twice as long to determine if to count all of those matches. So it's true that it's linear time no matter how many times it actually matches, so we don't need to get too involved in whether or not this if runs or not. Alright, let's look at another problem. Let's look at, I want to swap two elements in an array. So let's swap two elements in an array. Oh, I should point out, in general, we're going to look at best case versus worst case versus expected or average case pretty frequently. So this notion will come up often, and sometimes the best case time will not be the same as the worst case time. Alright. So now I want to swap two elements. So I have an array, and I have two indexes. We'll say index I and j. And my job is to swap the element at I with the element at j, and I'm going to assume that we already are pretty comfortable with swapping elements in an array, so I'll just code this up pretty fast. The key is that I get the value at index I, and I save it into some temporary place. My values are integers, so my temp is of type int. I save that value at I, but now that I've saved the value at I, it's safe to overwrite it with the value at j. So now I've taken the value at j and stored it in I. So now I want to do the same thing. I want to take the value that was at I and store it in j. But the value that was in I I've already overwritten, so it's an excellent thing I've already saved it in this temp. So now I've swapped these two values. Alright, having swapped the two values, the question is, how long does this method take to run? And now it occurs to me that swap doesn't actually return a value, it just has a side effect of changing the contents of the array, and specifically changing the order, so that should be void. Okay, I want to swap these two elements. How long does it take to perform that swap? Does it depend on the length of my array? Well, if I look at this, no matter how long my array is, I have 3 lines of code to run, and none of those lines depend on how long my array is, so the time for this is, again, constant. This operation runs in constant time. Now let's leave that up, and we're going to consider another operation, and we'll see if that runs in constant time. Let's make some room for it. This operation is going to be called bubble, and the first thing I should give us an example of what bubbling means, and this is not actually, at first this is not going to seem like a useful thing to do. In the bubble algorithm, I will swap the first and the last, swap the first and the second value if they're out of order, meaning I want to, if my first value is less than my second value, I will consider that to be in order and I won't swap. But if my first value is greater than my second value, I will swap them because they'll be out of order. And then I'll swap the second and the third value if they're out of order. And I'll keep doing this until I get to the end of my array. So let's actually look at an array and see what happens. Suppose my array contains 3, 2, 6, 7, 4, 1, 5, 8. Those are my array values, and I want to perform this bubble algorithm. So first it says swap the first two values if they're out of order. Swap the first and second value. Well, the first value is 3, the second is 2, and indeed they are out of order because 2 should normally go left of 3 if I write my numbers in increasing order and read left to right. So I'm disappointed to see 3 before 2, so I'm going to swap 3 and 2. In fact, maybe this will be easier if I actually just literally rewrite the 3 and the 2. Here's 2, and here's 2 and 3. Okay, so I swapped 2 and 3. But that's just the first step in the algorithm. The next one says swap the second and the third if they're out of order. Well, they're in order, so I'm happy. 3 and 6 can stay as is. Then I compare 6 and 7. They're in order, so I leave them. 7 and 4, but they're out of order, so I should swap the 7 and the 4. And now I compare 7 and 1. They're out of order, so I'm going to swap them too. So notice that 7 has now moved 2 positions. And then I swap 5 and 7, because they're out of order. And then 7 and 8 are in the right order relative to each other. And actually, if we think deeply about this bubble algorithm, it actually achieves taking the highest value in the array. In this case, it was 8 and it was already in the last position, but it takes that highest value and moves it to the last position. And notice 7 sort of bubbled its way toward the end of the array, and if we keep running this, some interesting things will happen. But let's code it, and let's look at the running time. So, the code for that, let's see, public static void bubble, which takes in an array, and we're going to, well, clearly we need to loop over the array. I'm aware that what I've written here is not entirely correct yet. And I need to, let's see, I'm supposed to compare the first and second element and determine if they're in order. So if AI is less than AJ, well, if, or no J, if AI is less than the value at the next position, which is I plus 1, and if the value at AI is less than the value at AJ, then they're in order, so there's nothing to do. So the interesting case is if they're out of order. If AI is greater than AJ, then I'm supposed to swap, and luckily I've already written a swap method. So I will swap the value at I with the value at I plus 1. And that's bubble, except that notice, because I'm comparing I and I plus 1, I shouldn't go all the way to the last possible index. I should actually stop one short of that. Another way to think about that is, if I have 10 elements, there will be 9 pairs to compare. So I should go one less than I usually go. Alright, that's bubble. Now that actually, if I think about it, I could have determined the running time before I even wrote this code, right? I should be thinking to myself, well, the time clearly depends on the length of my array, because the longer it is, the more comparisons I make. And if it's twice as long, I make, roughly speaking, twice as many comparisons. So that's the sign of a linear time algorithm. The time is proportional to the size of my problem, the length of my array. And when I look at the code, I can see that, yes, lo and behold, when the length is twice as long, I will get to this if twice as many times. I'll potentially get to the swap method twice as many times, and so the time will take twice as long. Note, though, part of my analysis depends on knowing how long swap takes. Because I know that swap runs in constant time, I can therefore conclude that since this runs in constant time, that I'm now calling a constant time operation, swap, a linear number of times. Overall, my running time will be linear. If swap were not constant time, then this algorithm is not going to run in linear time. It's going to be worse, and we're going to see that in a moment. But we'll pick up with that in the next video. I'll see you there, where we'll continue talking about this bubble algorithm and running times.